Welcome back to the 7th video about the MEMSIC MM5983MA 3-axis precision magnetic sensor. In the last video we covered the few remaining bits here in the control registers that are responsible for either automatically or periodically setting the magnetization of the AMR sensors in that thing. And we also started to have a look at the AMR Wheatstone bridge offsets that thing can actually measure using its set and reset operation. Card here, link in the description. And I promised you back then that we will talk today about temperature compensation, to be more specific, temperature compensation for these Wheatstone bridge offsets we measured last time. So enjoy! We already had a look at this very brief using set and reset to remove bridge offset chapter in the datasheet. Video already carded, link in the description. And I won't repeat all that stuff, just watch the second part of the previous video again. I will pick up where we left off there. Anyway, we already know that we can use a set and reset to remove the error associated with bridge offset. But here comes the second more important part: bridge offset change as a function of temperature, and thereby enabling more precise heading measurements over a wider temperature range than competitive technologies, blah, 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 blah. The question is, how big are these bridge offset changes, as a function of temperature? To measure that temperature drift, I wrote a relatively complex script, but I also added one convenience function to our library here. And I have also here a new type, which is simply an array for the raw access 18-bit data inside a struct. We did the same for that QMC magnetic sensor, that awful thing, but the technique is the same. Anyway, card here, link in the description. Then we have a new convenience function here, public of course, raw access output 18-bit array, which returns just that struct here. And it's simple. It just calls 3 times for each of the 3 axes, our raw access output 18-bit function with the axis, and fills up the array in that struct, and then it returns that struct. That's it. Now for the sketch, nothing special, we just do a begin here, and the intent is to print out later on the temperature, our 18-bit middle value, so 2 to the power of 17, and then the offsets for the X, Y and Z axis. In the loop we have now 2 of these raw access output 18-bit arrays, one for the values with the magnetization of our AMR sensors being set in the default direction, and one for the values of our 3 axes with the AMR sensor magnetization reset, that is reversed. We also have here a byte axis, which I will use in a loop. Then we do a delay 100 and we take a temperature measurement with error handling, everything of course. Then we do a delay 10 and we read out our temperature output, and with error handling of course. Then in an if statement, for now always true, we set the sensor magnetization and we wait until that's done, and then we take the magnetic field measurement and we wait until that's done, and then we read our axis output, and then we assign our values set to our raw axis output 18-bit array. Then we reset our sensor magnetization. We delay again until that's done. Then we take again a magnetic field measurement. We again read the axis output and we store the result, the measured values, in our values reset. Then we print out the temperature in Celsius times 10. Yeah, I did a little bit of scaling here, plus our 2 to the power of 17. That's just that it appears in the serial plotter in a nice position. Then we print out our 2 to the power of 17 value. And then we go through a loop for all our 3 axes. And in that loop, we print out the offset for each axis, and that's it. Let's have a look at the serial plotter. Now, we've already seen in the previous video that our readings, our offsets, that would be that curve here, the little noisy curve, and that curve, are basically unfazed by the total reading of each sensor, the absolute reading, but they get problematic if you really move the sensor around while you do the measurement. And we also talked about that video already, carded link in the description. Anyway, these are our 3, our Z, our Y, and our Z axis. Then we have here the temperature curve in blue and a little bit scaled. That's not really degrees Celsius. And here we have our 2 to the power of 17 curve, which would be the mathematical middle of our 18-bit value. So you can already see our Z sensor is far cry off with this 0 point from the ideal. Anyway, if I heat things up now, you see the temperature is rising, and so are our offsets. And it's completely different for each, well, not completely different, but it's more notable on the Y sensor and the Z sensor. The X sensor is obviously of a little bit better quality, so the rise is not as significant. And if we cool things down a little, you see the changes in offset are actually enormous. So temperature compensation for those Wheatstone bridge AMR sensors is a real thing. Well, a necessary thing if you want to take precision measurements. Now I want to take some data so I can actually show an offset over temperature curve in Excel for all 3 sensors. So I changed my loop a little bit. I have now here a static float temperature, which is initialized the first time we go into the loop with -76 degrees Celsius. That's 1 degree below the minimum value our chip can measure. And then I've added here in the if temperature is smaller than our actual temperature, then and only then I go into my if statement and print out some data, and also at the beginning I set the temperature to the actual temperature. And I think further down I'm still using here the MMC temperature Celsius, but it doesn't change in between. So we are in the serial monitor, and I first cool that thing down as much as I can. Then I press reset. And now we see the thing heating up again, slowly but surely. Hopefully. So we were at minus 35 degrees. I didn't thought I can get down that much. You see the stuff is still evaporating and now it's just ice, water ice here. I hope I don't get a short, and temperature is rising and we get some data. Wonderful. Yeah, I probably cut at some point here the video and tell you when we are back to 25 degrees, okay? Okay, we are at 18.3 degrees and I think I will speed things just a little bit up now. Okay, let's leave it at that. That's our lower part of the curve. From minus 35, I think it was, up to 27. I will now use my hot air soldering tool to heat things up a wee bit more. And yeah, hopefully, yeah, it's nice and cozy. Okay, that should be enough. We don't need to go to the full, 125 degrees. And here are all the numbers as a nice graph. So we have the temperature down here between minus 35 degrees and a little over 100 degrees. Blue is our 2 to the power 17, ideal offset or 0 point. And then we have red, the X offset we measured, green, the Y offset, and lilac, the Z offset. And right away you see the X offset is a little bit misbehaved. I saw some oddities with the X channel lately, and my best guess is that in the previous video when we checked out some undocumented bit settings in the control registers, I somehow damaged the X channel. But yeah, that's for another day. Anyway, the changes over temperature, even if we look just at the area between 0 and 20 degrees, they are enormous. And it's not really linear, so we cannot really extrapolate just between 2 points. You see there's a bump here. And the higher temperature range, about between 70 and 80 degrees, we get these irregularities, which are repeated up here between 90 and 100 degrees. And by the way, when I heated up the thing with the heat gun, I was a little bit too fast here at the end, so we don't have a tick really for every least significant bit. Anyway, for real temperature compensation, we would have to store all this data somehow. And we wouldn't need a 30-bit integer here. I mean, these offsets would, if you subtract the 2 to the power of 17 would all fit into a 16-bit integer, so easily plus minus 32,000, no problem. So to store a complete offset table for each temperature we can measure, and that's unsigned byte, so 256 different temperatures between minus 75 degrees C and 125 degrees C. We need 256 times 6 bytes, so 3 16-bit integers, so 1536 bytes or 1.5 kilobytes. That's a lot. However, the operating temperature range of our chip is only from minus 40 to plus 105 degrees Celsius. And a temperature compensated offset table for that would only need 186 entries, and that would leave us times 6 bytes at about 1116 bytes, so a little less than 1.1K. That's better. And considering that using that spray here, I was only able to cool that down to minus 35 degrees Celsius, so total range of 179 values, we would end up at 1074 bytes, so a little more than 1K. Bottom line, that compensation table, if we use one, should be flexible, yeah, not a fixed size. But what if we could eliminate that table altogether by just minimizing the error when we are measuring the offset while the sensor is moving or the magnetic field is changing? And for that, to test that out, I changed the loop again. We do some switcheroo stuff again. So I have my static unsigned integer here, and that's incremented. We saw that already several times, each time in the loop. And at 0, I switch the bandwidth to 100. And this means we need a delay of 8,000 microseconds before the measurement is finished. Then at count 50, I switch to 200 Hertz, and we need a delay of only 4,000 then. At count 100, I switch to 400 Hertz, delay 2000 microseconds. And then at count 150, I go to 800 Hertz. That was that very noisy but fast mode. And the delay is now down to 500 microseconds. And at 200, I start from the top again. The rest of the loop is only slightly modified. We no longer have an if statement here. We are printing out each time our measurements. And I do a set sensor magnetization, and I went down here with the delay before I take the field measurement to the absolute minimum, 1 microsecond. Then I take the magnetic field measurement and I wait only the minimum required delay. I read my axis output and I store my values for the magnetic field set in the sensors. Then I reset minimum delay and then take magnetic field measurement, then the prescribed delay for the bandwidth we are in. Read axis output, store the reset values in some variable, and then I print out the stuff again, without the temperature this time. I won't vary the temperature, I will vary the bandwidth settings. And our baseline here, our 2 to the power of 17, is modified by adding the delay minus 500 and divided by 10. This should give us in the serial plotter a nice stepped curve here. Let's have a look. So here's the output, and here we have our stepped curve starting at a bandwidth of 100 Hertz with a delay of 8 milliseconds, then going down to 200 Hertz, 4 milliseconds, 400 Hertz, 2 milliseconds, and finally here when it's all down at 800 Hertz, 0.5 milliseconds. And yeah, first of all, you can see that between the different bandwidth mode, especially here, when we're going to that very fast mode, there is a little jump in the offset. So that's a bummer. And the jump is not within only the noise. The jump is very visible here, at least for the Z-axis and the X-axis. And now let's do some movements. I try to be consistent. At minimum bandwidth, we have, of course, the largest errors, and then the errors go down indeed. But I fear, depending on the axis, even at the lowest, I'm moving it now in another direction, even at the highest bandwidth setting with only 500 microseconds delay, we still have, yeah, errors that are far, far beyond the noise level. Okay, that's not nice. You see, if I, instead of jerking around that thing, just move it continuously. Yeah, I would have to move it really fast. Well, yeah, here in the 800 Hertz mode, you can see it. If I go slower, the error resides. So yeah, we could work actually without the table. You see it here? What just happened there? No, I think filtering is not really a good method. We need a table. I'm sorry, we will need a table. So we need our offsets over temperature somehow in an array that we can insert into our C++ code. And I'm here in the loop basically back to almost the same code which we used to create those offset curves over temperature with some slight modifications. First, the temperature variable is now an unsigned int 8. And I'm no longer using the Celsius value, but I'm really using the raw temperature output value here. So that byte value between 0 and 255. Everything else is basically the same, but for my output here, the serial print stuff. So I start here every time the temperature has increased one least significant bit with a bracket, and then I print out my axis values. But this time I subtract 2 to the power of 17. So I really only get the, hopefully within a 16-bit signed integer value delta to that 2 of the power to 17. And yeah, in between, while I am inside my array of 3 values, I also print out a comma, and then I close the bracket and I have another comma because I have a lot of these triplets, one for each temperature, and then I add a little command here at the end with the temperature, the byte value, so that's my array index. And in addition, I also print out the temperature in Celsius just in that command line. We will see in a second how that looks in the serial monitor. And here you see the first line. So this will be a 2-dimensional array of 16-bit integers. Just the first line. Let me heat things up a little bit. Yeah. And then we need another opening bracket and a closing bracket, and we're done. And we give that a name and store it as a constant integer array or something. I won't do the measurement stuff online because you already saw that, and there's nothing new to learn. See you in a second or so. So, and here's our constant int 16 signed offsets values array, 2-dimensional, second dimension of course 3 for the 3 axis, and as you can see it's quite long. Yeah, we said it would be a kilobyte also of data in the code in the end. And yeah, I ended up measuring up to 102.3 degrees Celsius, but I only managed today to cool it down to minus 24 degrees Celsius. And I'm a little bit critical about these values here. Let's have a look. Now, these were the offset values over temperature we initially measured. And that's my new measurement here. And you can see, yeah, it's very similar, but we lost these artifacts here at the higher temperature range. So this is probably just a measurement artifact. But in turn, these first values here at minus 25 something degrees, they are clearly off. So I will throw them away. But otherwise, very similar. That's good, because that means it's repeatable. So I throw that first line here out of my array, and you see it's yeah, unrealistic jumps here. Something went wrong with the temperature measurement or whatever. I mean, I'm not using you know, a climate change chamber where I can control the temperature exactly. I'm using cold spray and a heat gun. Anyway, my offsets start at temperature 66, so minus 23.2 degrees, and they finish, and these are just bytes here, at temperature 226, if I'm right. Let's scroll down. Yeah, at 226, so 102.3 degrees Celsius. Now, what can we do with that table? In the private part of my class definition, I added 3 new variables, analog to what I've done in the sketch: offset starts, offsets finished, and that array of arrays, offsets values. I also have here, for initialization purposes, an offsets defaults 3 array, which just contains 3 zeros, so 0 offsets. I extended my constructor here with initializations for these 3 variables. So offset start is 0, finish is 0, and values is just the pointer to that offsets defaults array. So yeah, nothing is dangling anywhere with invalid values. Then I added a few public functions to my class, the first being set offset values, which gets the arguments offsets start, finish, and values. And that method does nothing else than assigning these values to my class variables. And then we come to the core of the things. Two new public methods here: raw access output 16-bit offset and raw access output 18-bit offset, which work analog to our 16-bit signed and 18-bit signed methods. Internally, they work, of course, a little bit different. So here we have the raw access output 18-bit offset. And I have here a local variable, just a byte temperature, and I read the temperature from my temperature output register. So the temperature has to have been read from the chip for that to work. And if the temperature is smaller than offsets start, or it's greater than offsets finished, then I just return the raw access output 18-bit signed. So with the default 2 to the power of 17 offset. Otherwise, I take my raw access output 18-bit signed and subtract my offset values for that temperature and that access. The raw access output 16-bit offset works exactly the same. The only difference is here that I downgrade my offset values here from the 18-bit values two 16-bit values, and I'm using the raw access output 16-bit signed. Now, in the setup, I tell now the library to use my offset values. Yeah, we already saw the definition. Here's the rest of the array. And in the loop, I have here a little byte access. I need that further down. I wait for 100 milliseconds. Then I take a temperature measurement. I wait for 1 millisecond. Then I read the temperature output, error handling, etc. Then I take a magnetic field measurement. Then I read my access outputs. Delay in between, of course. And then I print out all the axes, X, Y, Z. First, the raw access output 18-bit signed, and then the raw access output 18-bit offset. Let's have a look at the serial plotter. So, it's a lot of curves, 6 to be exact, but yeah, you can probably see which curve is which. So we have our X and our Y curve, these two here, which do the usual sine dance. And if I did my rotation nicely, you would see the two interleaved sine curves properly. Yeah, here we go. And I have, yeah, the Z curve is doing not much. I have to wiggle that here in the other direction. But the important thing here is, and let me just, yeah, choose here some nice values. And am I still in frame here? Yep. Let's wait a second until that stuff here is out of the frame. Okay, the question now is, what happens when the temperature changes suddenly? I mean, we wanted to do, oh, that was just me opening that thing. Hey, magnetic distortion. Never saw that before. Anyway, let's cool that down. It's easier than heating it up. Let's give it a few seconds. And then have a look-see. And you see here very nicely at the, I will stop it in a second now. About now. You see here, that's our compensated, our temperature compensated curve. And yeah, while I spray that thing up, I disturb the magnetic field and everything is a little bit disturbed. But you see, this is our compensated curve here. And it's absolutely unfazed by the temperature change. While lilac here, our uncompensated curve for the z-axis, it drops and it only slowly recovers as the temperature of our chip rises again. We don't see much action here on the X channel. You remember that graphic, the X channel temperature offset, and the X channel is a little bit meh, is not so nice. But you can see the same effect here on the Y channel. So that yellowish line here, that's the compensated curve. And after the disturbance is over, it's unfazed. It just continues on. While the uncompensated curve here, it goes also through that disturbance. And then it only slowly recovers after the temperature is rising again. So yeah, we successfully temperature compensated or offset compensated our little chip here. Yeah, great. Short addendum. You can see here where the curves suddenly match again. That's when we fall back to the default 2 to the power of 17 offset in our offset functions. That is, the temperature here went below our offset table. So this time I was obviously able to cool it down below 26 degrees Celsius. Yeah, just that you know what's happening here with these hard changes. That's it for today. We successfully temperature compensated our little AMR magnetic sensor here, which I intend to use for compass purposes. And we also learned that you shouldn't put spray cans near your compass. Yeah, for some reason this is really disturbing the magnetic field. Next time we will actually calibrate that thing. We've already done that with that QMC chip, card here, link in the description, but to get really good compass reading out of such a chip you need a calibration, and that's what we will do next. Till then, bye.